So I'm starting. I think it's Friday in Middle East, so people are busy. Anyway, we did all of this. We did the offer principle. We did subshells, uh, and we did how the subshells are going to be filled. We did that an S subshell only has one s orbital, two electrons, two electrons. The P subshell has three orbitals, three p orbitals with different directions. So six electrons, two electrons, six electrons. The D has five subshells, five orbitals, sorry. So it can accommodate a maximum of 10 electrons and so on. So you just follow the offer principle and you'll get the electronic configuration. So we did write the electronic configurations of different atoms, and then we did the two special cases as well, that copper and chromium. Like if you follow the offer principle, the electronic configuration is almost correct. The 4s is filled, then the 3d is filled, and except that the 3d instead of having 9 electrons would have 10, and the 4s instead of having 2 electrons would have actually 1 electron. And the same goes for chromium, that instead of it being 4s2 and 3d4 following the offer principle, it's instead 3d5 and 4s1. In this case, the half-filled and completely filled electronic configurations are considered to be more stable. So they are a more stable electronic configuration instead of the original off-bow electronic configuration. 3D9, you just completely fill it. You make it 3D10. Instead of this being 3D4, you make it half-filled, so that each of the orbitals is going to have one electron each. So we did all of this and we wrote down electronic configurations of different atoms. Now also remember one thing, that the periodic table is divided uh, into groups, plus there is transition metal. Transition metals are somewhere in the middle, and then you have your the rest of the groups. The rest of the groups are 3, 4, 5, 6, 7, and I think this should be 8. Anyway, so you have all these groups. So I'm going to link the electronic configuration to those groups. This one is group 1. And then I have my group 2. Then I have, this is, instead of calling this transition metals, the correct terminology for this is D block elements. And similarly, group 1 and 2 are called S block elements. And your after the D block elements, group 3, group 4, 5, and 6, 7, and then you have your noble gases, which is 8. I mean, from now on, this is 13 actually. This is in your periodic table, this is 13, this is 14. Yeah, this is 15, 16, 17, and 18. These are known as P block elements. So whenever you see a periodic table, you can kind of figure out the electronic configuration, because P block elements are those elements where the last electron ends up in a P block, in a P subshell. D block elements are those elements where the last electron ends up in a D subshell, according to the off-bow principle. And the same goes for this one. These two are S block elements. Why? Because the last electron ends up in the S block, in the S subshell. So I mean, you can try writing electronic configuration of different elements in P block. For example, you've got bromine, which is 35. So if you try and write the electronic configuration using the off-pop principle, which is this one, if you follow this order, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, and 4p5. So that's 35 electrons. So according to that table, it's 1s2, 2s2, 2p6, then 3s2, then 3p6, then you have 4s2, and then you have 3d10, and finally you have, according to the table, it's going to be 4p5, and I think that is going to lead to, that's a total of 15 electrons. So I filled the orbitals subshells according to the order that they're given in the off-pop principle. So the last electron ends up in a P. Similarly, take another element in group 6. Let's say you've got oxygen. Oxygen's electronic configuration would be 1s2 and 2s2, and then the last 4 electrons would end up in the 2p subshell. So then you're going to have another one, which is let's take another one. For example, sulfur. So it's going to be 1s2, 2s2, 2p6, 3s2, and then there's going to be 3p. What I think that's 4. As anyway, so that's P block elements. For D block, the last electron always ends up transition metals. Remember, not all are transition metals. I'm going to write it in. Most of them are transition metals, but not all. So the correct term for them is D block elements. Because transition metals have a particular property. I mean, they've got 5 properties: that they have high melting and boiling points, they form colored compounds, catalysts, etc. So not all have those properties. So D block elements, correct terminology is D block elements. So if you pick any element in the D block, according to the off-pop principle, the electronic configuration would be, it would end up in the last electron would go in the D subshell according to off-pop principle. So it's going to be 2p6, 3s2, 3p6, then there is 4s2, followed by 3d. There would be 6 electrons in the 3d. So the last subshell that we filled up according to the off-pop principle, the table that we had, the last electron went into the D subshell. And the same is true for S. Lithium is in group 1, so that's just 3 electrons. It's going to be 1s2 and 2s1. Last electron went into an S. Potassium is 19 electrons. You write the electronic configuration, it's going to be 1s2, 2s2, 2p6, and 3s2, 3p6, and then there's going to be 4s1. So according to the table, the last electron goes into the 4s subshell. So is this point clear? And is this clear, Alicia?
Yes, sir.
Now, the other thing is, you can learn a lot about because you can't really always write electronic configurations every time, because it's time consuming and you might forget the table. So you might have to, where's the table again? You might have to draw this table to figure out the order in which the subshells are getting filled. So I mean, it's time consuming. A periodic table tells you a lot of information. Just like this, a periodic table is able to tell you a lot of information about the electronic configuration of elements. So one such information is that, I mean, one information that you studied in O-levels was that when you look at a periodic table, group number tells you the number of electrons in the outermost shells. So that gives you an idea of the valence electrons. I mean, for example, group 1 is going to have 1 electron in its outermost shell. So for example, potassium over here is in group 1. So the outermost shell, which is the 4th shell, that has 1 electron. So that is the most energetic electron. That would be the furthest away from the nucleus. So it would be very far from the nucleus. The other electrons would be less energetic. They would be closer to the nucleus. Remember, shells are energy levels. Or in other words, shell uh, represents how far the electron is, because if the energy level is high, the electron would be very far from the nucleus. So one information that we got was the group number was the electrons in the outermost shell. And then you got some information from the period in which the element existed. So the period would tell you the total number of shells. So if you have an element like chlorine, which is in group 7, it's going to have 7 electrons, and chlorine is in period 3, so that means it's going to have a total of 3 shells. So this is some information that you got. Now, in this electronic configuration, you also get some information, and that information is that every time the electronic configuration of the outermost, so this is group 3, 4, 5, and you have 6 and 7. I mean, again, it's 17 actually, and this is group 8, or noble gases. And this is D block. The correct word is D block. So what information do you get about the electronic configuration? That for the outermost shell, group 1 is always going to end up with S1. That's the outermost, that's the electronic configuration of the outermost electron. Group 2 will always end up with S2. Group 3 will be S2. The outermost shell would be S2 and P1. Group 4 would be S2 and P2. Group 5 will have 2 electrons in the S and 3 electrons in the P. 6 will have S2 and P4. 7 would always have S2 and P5, and the last one, group 8, would always be full. So for example, if I have silicon, that's 14 electrons, so it's going to be 1s2, 2s2, 2p6, and there's going to be 3s2 and 3p2. So the last, or the outermost shell, or the highest energy electrons, I mean remember, there's no physical thing called the shell. This just represents the energy levels, which means that the electron would be furthest away from the nucleus. So it's going to be really on the outside. So the last shell is going to have 2 electrons, S2 and P2. So you can predict the electronic configuration of the atom by just looking at the group number. So nitrogen is in group 5. So automatically you should know that if it's in group 5, the outermost shell of nitrogen is going to have 2 electrons in the S, and there are going to be 3 electrons in the P. I mean, you can try and write the electronic configuration of nitrogen, 7 electrons, so it's going to be 1s2. That's the inner shell. Closest to the nucleus, 2s2, and then you have 2p3. So you can figure out that the outermost shell electronic configuration is S2 and P3. So is this clear? Alicia, clear? Anna? Zari, is this clear?
Yes. Yes.
Yes.
So just remember, not every time you have to actually write the electronic configuration. For transition metals, the outermost shell is mostly S2. You write the electronic configuration of any transition metal, the outermost shell, for example, iron over here. The fourth shell, which is the outermost electrons are going to be in S, and there would be 2 of them in that. But there were some exceptions. The 2 special cases were copper and chromium. Their outermost shell was actually S with 1 electron in it. So not all D block elements are going to have the same electronic configuration. Exceptions are chromium and copper, where the electronic configuration would be S1. So by just looking at the periodic table, I mean, you should know what information. Don't write the electronic configuration, don't write the whole entire electronic configuration. You'll just figure out what the outermost shell would look like. Because this is the outermost shell, that's the one that's actually taking part in the bonding. These are the electrons that are the most energetic electrons, that they're further away from the nucleus. And also remember, what other information that you get? You get group number tells you the total valence electrons. which is also true over here. Like group 5 is going to have a total of 5 electrons, except that the 5 electrons are split up, 2 in the S and 3 in the P. And the period number tells you the total number of shells. Now we're going to do some past paper questions related to electronic configurations, and let me upload this just a second. Or maybe I can. I said this one, just the first 30 pages. Yeah, I actually opened the wrong one. I said we're going to do these questions over here. Okay, so I'm not on the board. We can try and start with electronic configurations, page 21. I said, so starting with the first one. Okay, so let's start with the first question. Now this says that there's an atom with 8 protons, so you're supposed to write the electronic configuration of the second shell, just the second shell, electron distribution in the second shell. So 8 protons means that it obviously has 8 electrons, and he's referring to an atom. Remember, be careful. Is he referring to an atom or an ion? And I'm also going to add, and let me delete this. So I'm also going to add that electrons, when ions are formed, we didn't do ions. So in this, we can add, okay, when ions are formed, electrons are always added or removed from the outermost shell, which is kind of obvious. So electrons are always added or removed from the outermost shell or the outermost subshell slash shell. I mean, for example, potassium is +1, so that means potassium forms a +1 ion, so that means the electron would be lost. If potassium becomes an ion, then the electron would be lost from the outermost shell. Iron, if it forms 2+, the electrons would be lost from the last subshell. If it forms a 3+ ion, then there's going to be 1 electron that would go from the 3D as well. Bromine forms a -1 ion, so if it forms a -1 ion, then the electron would be lost or gained, sorry, in this case, in the outermost subshell. So that is kind of obvious. Electrons are always removed or added from the outermost shell. So starting with this question, 8 electrons. 8 electrons would be 1s2. It's going to be 2s2. And you're left with 4 electrons, so it's going to be 2p4. Now he was asking for the electronic configuration of the outermost. The outermost shell is this one, the second shell. There's an s orbital, so that's a spherical one. So we do have an s orbital, s subshell, and we've got 3p subshells. So the orbital shape, we do have a p as well. In the p, we have 4 electrons, so that's going to be, so the answer is going to be b, that the p has 4 electrons and the s has just 2 electrons. So that's the answer to this one. As the next one is the electronic configuration of an atom of sulfur is given. How many valence shell and valence shell? How many valence shell? The first thing is, how many valence shell electrons do you have? So the valence shell starts from the third shell. You've got 3s2 and 4 electrons in the p. So those are the outermost electrons. So that's a total of 6. So it would be either one of them, C and D. And the number of unpaired electrons. So the total number of unpaired electrons. Now remember, all the other orbitals are completely full. The ones that are unpaired, the only one that's not completely full is 3p. So 3p has 4 electrons, and I told you that the subshell has 3 different orbitals. It's 3px, 3py, and 3pz. So, and I did tell you how to fill those electrons. How would the 4 electrons be filled in these? First thing is, 1 electron would enter each one of the orbitals, and then the 4th electron would come and occupy this one. So there would be 2 in this one and 1 each. Remember, subshells are always filled in a single manner first. So how many unpaired? This is paired, and I told you about spin pair. I told you about the opposing magnetic fields. Electrons in an orbital, if they are in a single orbital, they're always paired. Whereas this one and this one, they would be unpaired. There's only going to be 1 electron and 1 electron in this one. So the total number of unpaired electrons, that's going to be 2. The 3py and the 3pz are unpaired. So the answer is going to be D. So is this clear, this question? Aisha, is this clear? Alicia, Nabila, is this clear?
Yes.
So then the next one is, the question refers to isolated gaseous atoms. In which atom are all electrons paired? Now, it's going to be very time consuming if you start writing the electronic configurations of all the elements. So barium is in group 2. I told you that group 2 is going to be S2. That means its outermost shell is paired. The inner shells are all full. I mean, we don't care what the inner shells are. I mean, if I write the whole electronic configuration of barium, I think it's 37. So it's going to be, I'm assuming it's 37. It's going to be 1s2, 2s2, 2p6, 3s2, and then 3p6, and then there's going to be 4s2, then 3d 10, all of them full. This is a total of not sure how many electrons, that's 30. I'm assuming that's 30. Then there is 3p6, and then there's going to be, 4p6. According to the off-bow principle, there's going to be 4p6 followed by 5s1. 5s2 barium. Let me just check. What's the electronic configuration of barium? No, the atomic number is actually 56, so we just have to keep going. Like, barium will have a lot of electrons, so it's going to be really time consuming if you start following the off-bow principle and you start writing the electronic configuration of barium. So it's not going to end up at 5s1. It would just continue after that as well. So up till 5s2, that's 2, 4, 6, that's 10, and then there's 2, that's 12. Up till this point, that's going to be 30. Then there would be 36, 38, and then 10 more, that's 48, 48, that's 54. And then there would be 2 electrons over here in the 6s. So it's going to go up till the 6s, and it's going to be 2 electrons. But you don't need to actually waste time doing that by just looking at the barium atom. I mean, this just continues after this. It's going to end up at 6s2. But it's going to be very time consuming following the off-bow principle. So just remember, follow this rule. Barium is in group 2. So we don't really care what's the electronic configuration. We just know that the outermost shell, this one, it has 2 electrons. All the other inner shells would be completely filled. So in which atom are all electrons paired? The answer would be barium, because all the subshells are full, completely full. They're all paired. For bromine, they are not paired. It's in group 7. The electronic configuration of group 7 is, in the outermost shell, there's going to be an S with 2 and a P with 5. Now, if you've got 5 in the P subshell, then they would not all be paired. There's going to be 2 in this, and only 1 in this one. So same goes for sulfur. Sulfur is in group 4. Group 4 would be S2 and P4. So the P subshell is not going to be fold. It's not going to be paired. It's going to look like this. And the same goes for silicon. That's in group 4, and that would be S2 and P2. So the P subshell is not going to be paired. There would be 3 P orbitals, and there's going to be 1 electron, 0 electron. So there would be just 2 electrons in the P subshell. Is this question clear?
Yes.
So now the next one is, what is the electronic configuration of an isolated nickel 2 plus ion? Now I told you that, again, you have to do this very quickly. TK, you don't have time to sort of look at nickel. You just know that nickel is a transition metal, right? I just told you about transition metals. TK, nickel is somewhere over here. We're not going to spend our time writing the electronic configuration. About transition metals, I told you somewhere over here, this thing. So for D block elements, I told you that the outermost shell is going to have 2 electrons, except for chromium and copper, that's it. So it's going to have S2. If nickel is 2 plus, that means the 2 electrons in the S are also gone. So, I mean, if it wasn't an ion, there would be 2 electrons right in the outermost shell. But now it's 2 plus, so that means those 2 electrons are also gone. So nickel 2 plus is not going to have an S subshell. I mean, it used to have an S subshell, but there would be 4s2, but that would be gone. So the answer would be D, the one that's without the S subshell, because it's 2 plus. Then you've got, which statement about orbitals in krypton atom are correct? The 1s and 2s have the same energy level as each other, but different sizes. They don't have the same energy level, because that's the first shell, and this is the second shell. So the electron in the second shell is more energetic. It would be further away from the nucleus. So it's going to be like this, that what did the shells represent? The shells represented how energetic the electron was. So in the 1s, the electron is not very energetic, so it's occupying a spherical space very close to the nucleus, whereas in the second shell, the electron is more energetic. It's occupying spaces much further away from the nucleus. So the first statement is incorrect. They don't have the same energy level. The rest, if the first is incorrect, the second and the third are going to be correct. The third energy level has 3 subshells and 9 orbitals. So the third shell, he says that there are 3 subshells and 9 orbitals. We can just have a look at the Aufbau principle, where all the subshells are listed. So where did our Aufbau principle go? Just a second. That's this one. So third shell, you can see all the shells. The third shell has 3 subshells. I mean, it's got a 3s, it's got a 3p, you have a 3d as well. So you do have 3 subshells, and you have a total of 9 orbitals. There's 1 orbital over here, there's 3 orbitals in the p subshell, and there are 5 orbitals in the d subshell. So that makes up a total of 9 orbitals. So which is why this option over here, the second one, is correct. You do have 9 orbitals, and you do have 3 subshells, 3s, 3p, and 3d. Then you've got the 3d subshell has 5 orbitals that have the same energy level as each other in an isolated atom. The d is actually made up of 5 orbitals, which are 3dxy, 3dxz, 3dx square minus y square. There is 3dz square, and I think there's one 3dyz as well, which we did do. And I told you the shapes of the d are not important, but we did draw them. I told you that if an electron exists in the d subshell is made up of 5 of the d orbitals. Each one, the electron could exist in a different space, but they're lying on different axes. So now after that, you've got 31, which statement about orbital. I think we did this already. He's talking about which statement about the atoms of Na and magnesium are correct. They have the same number. Now, Na is 11 and Mg is 12. So that is 1s2, 2s2, 2p6, and 3s1. This one is 1s2, 2s2, 2p6, and 3s1. So they have the same number of filled electron orbitals, which is true because, this is 3s2 actually. One more electron. So they have the same number of filled electron orbitals. Let me read the other ones. They have the same number of neutrons, which is also, I think, kind of true. 23 minus 11 and 24 minus 12. That is correct. They're both reducing agents. Reducing agents are the ones that like to lose electrons. So metals, they're reactive metals, they do like to lose electrons. So that is also true. And number one is also true because they have the same number of orbitals. Both of them have identical orbitals. It has more electrons, but they have the same number of orbitals. You've got an isolated gaseous atom of element X has paired electrons in at least one of its 3D orbitals and has a filled 4s subshell. Now, there's a 3D orbital as well as a 4s. That's definitely a transition metal. It could be a transition metal, but it could be other substances as well. So, for example, iron, that's true. We did write the electronic configuration of iron. About transition metals, I told you that the last electron goes into a D, and the outermost always is 4s. We did write the electronic configuration of iron, which was somewhere over here. So I did tell you that the last electron ends up in a D and the 4s is filled in a D subshell. So iron is correct. Copper would not be correct. He's saying it has a filled 4s subshell. So for copper, remember copper is a special case. The copper's electronic configuration was 3d10 and 4s1. So the 4s is not completely filled. So that means it can't be copper. What about gallium? Gallium is, we're not sure where gallium is. Gallium is probably in, and let me open the periodic table. So gallium is over here. The electronic configuration would be that up till 30, it's 3d10, 4s2. You can write the electronic configuration, so it's going to be 3d10, 4s2, and then there is going to be, after 4s, there's going to be 4p, which would have 1. So the 4s and the 3d would be completely full. You can write the electronic configuration of gallium, and that is exactly what you're going to get if you write it. 31 electrons, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6. Then there's going to be 4s2. Then there would be 3d, that's 10, that's 30 electrons, and then you'll have a 4p, which would have 1 electron. So the 4s would be filled, and there is at least 1 electron in the D subshell. So gallium is also it's also correct. Is this clear?
Yes.
So which isolated atom has a total of 5 electrons occupying a spherically shaped orbital? So 5 electrons in the s orbitals. Starting with boron. Boron is I think it's 5. So it's 1s2, 2s2. It's lithium, beryllium, and boron. That's lithium is 3, 4, 5. Yes. So spherically shaped, or the S subshell. This has 4 electrons. Let's talk about fluorine. Fluorine would be 9 electrons. That's 1s2, 2s2, 2p5. Again, the spherically shaped orbitals only have 4 electrons. So now the answer would be sodium. It's going to be 1s2, 2s2. The 2p would be full, and then there's going to be 3s with 1 electron. So the spherically shaped orbitals have a total of 5 electrons. So hence sodium is the correct answer for this. So what else? For electronic configurations shown, with 3 of these electronic configurations belong to atoms of the elements chlorine, sodium. Now, you just have to identify chlorine. Chlorine is in group 7. Group 7 would be S2 and P5. So this is Cl. Sodium is in group 1. So that would be S1. So that is sodium. Now you're left with, he's saying there's vanadium as well. So you just have to figure out the electronic configuration of vanadium. Vanadium is in the periodic table, it's 23. So you can try and write the electronic configuration of vanadium, which is going to be, if you try to write it, it's I mean, you would have to write it. There's no shortcut. So for 23, it's going to be 1s2, 2s2, 2p6. And then there's 4s2. And then there's going to be, that's 20 and 3 electrons in the D. So it's going to be D3 and 4s2. So that is vanadium. So which electronic configuration belongs to an atom of another element? That's going to be D. Okay, is this correct? Clear?
Yes.
So here, let's continue in the next class then. Okay, I'll send the worksheet over. You can try and do the electronic configuration questions. So everyone take care. Allah
Right,
Hafiz.
sure. Thank you.
Allah
Allah Hafiz.
Hafiz.